H of S, GS H of S. Hina في denominator GS H of S. But since now H of S is equal to 1, that's why you will find it that we are writing it just simply J over 1, J over 1 plus JS. Here, in fact, it was a transfer function, the closed loop transfer function, C of S over R of S. So it should be simply J of S over 1 plus, because you know we have minus, so it will be plus J of S times H of S. This H of S is equal to 1. H of S is equal to 1. So we end up by having this equation number 1. On the other hand, as I mentioned to you, Sabab, C of S, the output, will be simply the error times G of S. Error times G of S. If we take only the circuit here, from E, G, and E, C, G, E, we will find that C of S will be simply E of S times G of S. Now, E of S can be written like this. If you solve for E of S, or if you substitute equation 2 into equation 1, if we substitute equation 2 into equation 1, we will find that we can write E of S like this one. I will substitute now in front of you. I will substitute equation 2 into equation 1. I will substitute it like this. I will write it like this. C of S over R of S. I will substitute C of S by E of S. We wrote C of S as EG, so I will write E of S times G of S divided by R of S equal to G of S 1 plus G of S. If you simplify G of S here and here, you will end up by having E of S will be R of S times 1 plus JS. So this is what you get. Exactly the same equation like here. Now, the steady state error, ESS, will be simply found by using the final value theorem in time domain. You remember, we were saying ESS will be limit when t goes to infinity of E of t. The final value theorem tells you that the limit when t goes to infinity is simply limit S E of S when S goes to 0. Limit S E of S when S goes to 0. We have E of S. We need just to multiply it by S. And if you multiply it S by E of S, this is what we will find. So if we multiply by S, so this will give you S E of S will give you this one. So if you look now to the steady state error, which is ESS, is known as the steady state error, it will depend on the input and it will depend on G of S only. So that's why we are saying equation 4 shows that the state error depends on the input R of S and the forward transfer function G of S. So this one, it does not depend on the overall transfer function or closed loop transfer function. It depends on the forward transfer function, which is G of S and R of S and the input. So since we have the input, we will see now what are the inputs that we can have. For example, for a step input, you remember in time domain, we write it R is equal U of t or 1 of t if you want. Here we have magnitude 1. And R of S will be simply 1 over R of S, 1 over S. Now the steady state error, we wrote it in the previous equation. We wrote it limit S, R of S over 1 plus JS. Now you substitute R of S by 1 over S in when we have step input. You simplify S with S, and you end up by having 1 over 1 plus G0. This G0, we call it KP. We call it KP, which is position error constant. It's position error constant. And the steady state error itself will be 1 over 1 plus KP. So the steady state error will be 1 over 1 plus KP for step input. And KP is known as the G0 or position error constant. Remember, we can write it like this. KP equal to limit J of S when S goes to 0, or simply it is J0, the value of J when it is equal to 0, G0. واضح شباب? So this is the position error constant, and the steady state error will be 1 over 1 plus Kp. If we have another input, like the ramp input for this equation, we have the ramp input. If you take the derivative of this one, you will get something constant, 1, like this. And this is known as the velocity, constant velocity input. It's called either ramp input, or if this is the displacement, V is equal to displacement is equal to T. So the C or X of T, the displacement will be T. So the velocity will be constant, and it will be unity. So that's why we call it constant velocity input. If we take the ramp input, Shabab, R dot of T, the rate of change will be 1, and Laplace transform of R of S will be 1 over S squared, as you know that. So similarly, we will look for what is the steady state error. The steady state error will be similarly S times R of S over 1 plus G of S, and take the limit when S goes to 0. This turns to be limit S over 1 S squared over 1 plus G0. If you simplify, Shabab, S with S squared, S will cancel and you will have 1 S in the denominator. So it will be 1 over S plus SG0. When S goes to 0, this guy will go to 0. And we will have the limit will be 1 over SG of S. We do not take this one to be 0, Shabab, هنا, لأنه maybe G of S will be 1 over S, and you can simplify S with S. So we are leaving it as SG of S. And this limit, we will call it 1 over KV. 1 over KV, ESS will be 1 over KV, where KV is equal to limit SG of S, and this is called as velocity error constant. KV is known as the velocity error constant. Velocity error constant. We had KP is, do you remember, position error constant, and now we are showing the velocity error constant. The position error constant will be G0. The velocity error constant will be limit SG of S. We will have also the parabolic or constant acceleration. تفضل يا هاني.
دكتور بس السلايد اللي قبل.
Can you raise your voice please? I don't hear you.
أقول السلايد اللي قبله.
تفضل.
زاد فضلك. دكتور هنا why we eliminate this? Shouldn't we differentiate it in the limit?
We did not differentiate. No, it's not 0. It's not 0 because G of S, this G of S, we did not eliminate it. We are not saying eliminate it. We are saying it is SG of S. لأنه G of S can take any form. مثلا, just an example. Example, if G of S is equal to S, 1 over S. G of S is equal to 1 over S.
Yeah, now clear.
It's 1 over S times 1 over S, and this one will be equal to 1. So
yes,
KP here will be equal to 1. So we did not say, we did not make anything. We are just saying this, we leave it as G of S, and we know we are saying it is KV. KV will be limit of SG of S, and it is called velocity error constant.
Yeah, now clear. Thank you.
Any question? Any question, Shabab? Similarly, we do for the when we have a constant acceleration, an equation like this one, parabolic form, 1 over a t squared. So the acceleration here will be constant, and لأنه acceleration يعني you differentiate it twice. If you differentiate once, you will get the velocity. If you differentiate it once, you will get 1. يعني unity acceleration. The acceleration here will be equal to 1. But Laplace transform for it, if you take Laplace transform of this one, it will be 1 over s cubed. Laplace transform will be 1 over s cubed. Now, We take similarly the steady state error will be limit S R of S when S goes to 0. So it turns out to be S R of S 1 over plus G0. It is 1 over S squared. You simplify S here with S cubed here, you will have a remaining S squared. This S squared will come here and will come here. So it will be 1 over S squared plus S squared G of S. This limit, the total limit, this guy will go to 0. But this guy will just leave it as is. We leave it as is and we call it KA. Depending on the expression of G of S. لو تكون G of S is equal to 1, G of S 1 over S, G of S 1 over S, depending on G of S. So it's better not to touch it and leave it like this. And we'll say the steady state error will be equal to 1 over KA, where KA is given by this, S squared G of S. Limit S squared G of S when S goes to 0. So far, remember, we defined the position error constant. We said this one will be equal to G0. We define the velocity error constant, KV, which is equal to limit S G of S when S goes to 0. And here we are defining the acceleration error constant, which is equal to limit S squared G of S when S goes to 0. So these are the three error constant. The steady state error for the first case, it will be ESS, will be 1 over 1 plus KP. The steady state error for the second case, it will be ESS, will be 1 over KV. And for the third case, it will be 1 over KA, like we are seeing it here. So remember these three things. Now, the type of feedback control, we have seen, Shabab, we can write the transfer function in the open loop transfer function G of S can be written in two standard form. Either in the time constant form, yani K times TS plus 1 over this T0 S, over Sn TPS1 plus TPS2. So the denominator is for the poles and the numerator is for the zeros. هنا شباب no matter what يعني when S goes to 0, when S goes to 0, this will be 0, this will be 0, this will be 0. Then you multiply by S. It's a constant multiply by S. Constant, all this will be 0. So if you look here at the end of the day, this will be J of S will be K over S to the power N. N will be the most dominant one. N will be the most dominant one. So here, the system type refers to the order of the pole of the JS at S is equal to 0. When S is equal to 0, we say the order here. For example, for this example here, the order is N. G of S is N. لأنه we have S to the power N. If I give you, for example, similarly, same thing here, we can write it in the form of 0 or pole. When S goes to 0, this will be 0. This will be 0, this will be 0, this will be 0, this will be 0, 0, 0, zeros. And then we will have this form. It will again depend on the S to the power N. So remember, the type, we are saying the type. I am not saying the order, Shabab. I am saying the type. If I write G of S like this, G of S will be equal to 1 over S squared plus 3S plus 43. What will be the type of this, Shabab? This is plus 3S plus 43. What will be the type of this? What is the type here? As an exercise for you, what is the type of this G of S?
Acceleration.
Shabab, what is it?
Acceleration error or?
No, type. We are saying type will be 0, 1, 2, 3, and so on.
2.
Let me bring the next slide. So with the gain, Hina, just pay attention. Hina, you will be able to answer this question. With the gain relation of equation 1, if we take the time constant, or we take the time constant form, we can write it in this form. Here, to the power n involves the denominator that correspond to the number of integration. How many integration? You remember when we studied Simulink, we were multiplying by 1 over s, and then 1 over s, and then 1 over s. This is called the integration. The integration is 1 over s to the power n. So this equation here, as s goes to 0, this term dominates the determining of the steady state error. كل هذول will go to 0, 0, 0, 0, 0, 0. So 1, 1, 1, 1, 1, 1, 1, s to the power n will be the most dominant one. And then we say the n is the order, not the order, but the type. N is the type of this equation, type system. That's why we are saying control system are therefore classified in accordance to the number of integration in the open loop transfer function as described in the following. So this one will be the open loop transfer function, G of S. System type 1, system type 2, system type 3, and so on. So just before we go to the next slide, I'm giving you here G of S. G of S, I will write it in, I don't know what's your preferred color. I never ask you, but I am changing the colors. I don't know which one you like. And usually my preferred color is the navy. GF is equal to 1 over s cubed plus 3s squared plus 2s plus 19. Can you please tell me what is the system type of this equation?
Third type.
Here we have s cubed.
Third type.
Here we have s cubed, Shabab. What is the order of the type, system type? I am asking you now, what is the system type? System type. Okay, what is the system type, Shabab? I heard one answer, 3. Any other answer? 3. Any other answer? Any other answer, Shabab? I heard 3. Three. Any other answer, Shabab? Any other answer? So the system type is, system type here, as you can see, is 0. System type is 0, is not 3. Why? Because I'm not writing here. I can write it, to write it in this form, I should write it s to the power 0. I cannot take s common here. It is basically, it's s to the power cubed plus 4s squared plus 2s plus 19. S to the power 0 is 1. So the type is s to the power 0. You need to have this integrator shown. This is, order is 3, yes, but the type is 0. Remember this, type, system type is 0 here. Let me give you this equation again. G of S will be equal to this G of S. And again, here, Shabab, it depends on G of S, is not on the transfer function, the closed loop transfer function. Now, I want you to give me the system type of this. S cubed plus 3s squared plus 2s. What is the system type?
1.
System type, Shabab. System type is equal to 1. I can write it like this. I can write it s times s squared plus 3s plus 2. So the system type in L integrator is 1. That's why we are saying s to the power n. Remember, this is system type 1, but the order, what is the order, Shabab? The order is 3. And you need to decide this from G of S, which is this one. The G of S is this one. This is C of S, the output, over R of S is the input. You should decide from here. So the system type is defined from this, from G of S, not from C of S over R of S. واضح شباب? So now, if this is the case, if we take a type 0 system. Type 0 system, the transfer function at the end of the day, g of s, can be written like this, k over s to the power 0. صح؟ لأنه this is the most dominant one. K over s to the power 0, it will be k, the most dominant one. Now we will look to the steady state error. The steady state error to various input, we found it before. We found it for the position. It was 1 over 1 plus k هنا g0. It will be 1 over 1 plus g0. لأنه my equation هنا will be g0. This g0, we call it 1 over 1 plus k or 1 over 1 plus kp like we defined it. So this منتهية, finite value depending on kp. For the velocity, we found 1 over s plus g of s. Remember, my g of s هنا is equal to k. In this case, it is equal to k. So 1 over 0 multiplied by k will be 1 over 0. 1 over 0 will be infinity. This is equal to infinity. Similarly, for the acceleration, we have 1 over s squared g of s. G of s هنا is k, simply k. 1 over 0 will be infinity also. So the steady state error for type 0 system, for type n is equal to 0, type 0 system has a constant error. This is constant, finite value. It is infinite velocity error, infinity, and infinity for the acceleration error. So this is when we have type 0 system. For type 1 system, J of s will be k over s to the power 1 or k over s. Here, if we write our G0, it will be k over 0. G0 will be infinity. So 1 over infinity will be 0. It is finite. Finite يعني ما منتهية. 1 over now, when g of s is equal to k over s, here just substitute j of s by k over s. So I will have 1 over s, k over s. Simplify this with this, it will be 1 over k. 1 over k, we call it 1 over kv. So it is finite. It has value, finite. Now, when we have this, the acceleration, it will be 1 over s squared g of s. Just substitute g of s by k over s. You will have 1 over s squared and then k over s. You simplify s with s. 1 over 0 will be equal to what? Infinity. So the steady state error here will be simply infinity. 0, 1 over kv, infinity. As a summary to that, the system type N1 gives you 0 position error, 0. Constant velocity error, the error will be constant. And infinite acceleration error. Error will be infinite for the acceleration type. Yani for, if you have acceleration input, this will be your error. If you have velocity input, this will be your error. If you step input, this will be your error. تفضل يا هاني.
دكتور هنا الانفينيت acceleration error يعني it could be changing يعني minus positive مثلا ولا it goes to infinity ولا كيف؟ مش واضح يعني.
Infinite error. We will see it. Yeah. We will see it. Give me 1 minute. We will see it in the next slide, inshallah. Similarly, Shabab, if we have type 2 system, our transfer function g of s will be 1 over s squared. And you substitute here now, J0, you will substitute it by k over s squared. K over s squared. G0, when you take G0, k over s squared, so G0 will be k over 0 squared. K over 0 squared will give you what, Shabab? Will be infinity. So this value will be infinity. Huh? 1 over infinity, it is 0. The steady state error for type 2 will be 0. For velocity, we define the steady state error to be 1 over SGS. So 1 over S times G of S. You remember G of S is K over S squared. You simplify S with S, and you have K over S. K over S, it goes to where, Shabab? When S goes to 0. K over S goes to infinity. So it will be 1 over infinity, and this will give you 0. So 0 steady state error. And then you simplify here when you get 1 over S square G of S. You will take the error 1 over S square K over S square. You simplify S square over S square, and your limit will be simply, or your error will be simply 1 over K. We call it 1 over Ka, which is the steady state error for the acceleration input. So as a summary, a system with n is equal to 2 or 2 integrations, S square, yani 2 integrations, we have 0 position error, 0, 0 velocity error, 0, and constant acceleration error. To summarize all of these ones, you have this schedule here. In the schedule, this is what you can do, shabab, if you want. ممكن حتى تغمض عينيك. While you are closing your eye, you are saying from left to right input, unit step input, unit ramp input, unit parabolic input. Here we are saying unit معناته 1. 1 over K, the magnitude is 1. The system type 0, 1, and then 2. So you will take the diagonal. The all error will be in the diagonal. Diagonal, this, you are closing your eye and you are saying, oh, for type 0 and unit step, the steady state error is 1 over 1 plus Kp. For unit ramp input and for a system type 1 is equal to 1 over Kv. For a unit parabolic input, and we have type 2 system, it will be 1 over Ka. The upper diagonal will be infinity, infinity, infinity. The lower diagonal will be 0, 0, 0. When here we are defining Kp is equal to G0, position error constant. Kv is the limit velocity error constant, and Ka is the acceleration error constant. And this is how to find them. In a similar way, graphical way, this is what it is. Position error constant. The position error constant will give you a finite value, A over Kp. Here, A is simply the magnitude of the step input. So type 0 system position, this is the error. This is how do you understand the error. For the same thing, بالنسبة لهاني, type 0 system, and you have velocity input. This is the velocity input dotted line. The error will become large. As you can see, the error between the output and the input will be large. It is increasing. It is increasing and so on. For the acceleration input here, the error is becoming large, infinity. So this is what you have as input, and this is your output. The error is increasing. So we finish with type 0 system. We will go to type 1 system. Type 1 system, we are saying that the steady state error for system type 1 for unit step is 0. This is the error 0 here. There is no error. It will go when t goes to infinity, the steady state will be 0. And this is what we are doing here. For the, it is finite value. It will have a finite value when we have velocity input, A over Kv. So this one will be A over Kv. It will be 0.1, 0.2, 0.3. It is constant. For the acceleration input, it's increasing with time. So it will be infinity. The steady state error for the second type 2, for the position error, it is 0. Here it's 0 and here it's 0. So it is 0 also for the velocity input. As you can see, the output and the input when t goes to infinity, they will be the same. And it will have a finite value when we have the acceleration input. The steady state error will be A over Kv. A هنا شباب is simply the amplitude of the input. هنا it's simply 1, unity. That's why I'm saying unit, unit, unit. But you can put it A to be consistent with this one. So that's why we have A. Is this clear, Shabab? It's just diagonal. تفضل هاني.
Doctor, if we have like type 3, we will have all zeros, right? But is it achievable? I mean, the first
the most
beginning.
Important,
yeah.
The most important unit step or like input, usually in steady state error, we are taking these 3, 0, 1, and 2. When it goes to type 3, this is beyond the level of your course, beyond the level of the course, and we are studying in control. Usually, this is the most encountered, we see this one. This is what we find: 0, 1, 2, unit step, unit ramp, and unit parabolic. These are the most one that have applications in the industry and everything.
Yeah, I mean type 2. Like we take like type 2. Is it achievable to have zeros in velocity and position?
We will see. We will see this one when we will go to the lab. We will see how we can achieve this one. Yes, we can have the zero steady state error. See this. As an example, Shabab, they are asking you in the system shown in the figure, find the steady state error for the following inputs: 5 UT, yani 5 step input, 5 TUT, 5 velocity input, 5 T square acceleration input. And this is G of S. What is the system type from here, Shabab? If you look to this equation, what will be the system type? Can you answer this question? What will be the system type? Anyone can answer this question? System type, Shabab, Hina, is the number of acceleration. It's S to the power 1, so the system type is 1. When we have system type is 1, these are the errors, Shabab. Error for position will be 0. Error for velocity will be A over KV. Error for acceleration will be infinity. Now, if we look to this, this is what we have here. Kp will be a limit of Sg of S. You just take S is equal to 0, you will find Kp. This is 0, this is 0, this is 0, this is 0. 1,200 divided by 0, it will be infinity. So Kp will be infinity, and the steady state error will be 5 over 1 plus Kp, or 5 over 1 plus infinity. The steady state error will be 0, and this is exactly for the step input. This is exactly what we were expecting. Steady state is equal to 0. Next, we'll calculate Kv. What is Kv? Kv is limit Sg of S. So you multiply S times G of S. You simplify S with S and substitute S is equal to 0. So this will be 0. This will be 0. This will be 2, 6. 2 times 6 is 12. 12 times 100 is 1200. Divided by 12, or you simplify 12 with 12, you will find 100. So the steady state error will be constant. So it will be the steady state error. It will be simply 1 over KV, or 5 over 100. 5 over 100 will give you this one. It's the steady state error will be finite value. It has a finite value. It is 5 over KV. 5 over KV will give you this. 5 over KV or 5 over 100. 5 over 100 is 1 over 20. So the steady state error is finite value. Similarly, for the acceleration, if you remember, this will be S squared G of S. You simplify S with S. And no matter what you have, 0 multiplied by anything, it will be 0. And your acceleration error due to the acceleration will be 5 over Ka, or 5 over 0. It will be infinity. 5 over 0, it will be infinity. And it was expected from here. Infinity. So this is what we have in the steady state error. What we have seen so far, Shabab, it was when we have a unity feedback. This was the steady state error. Now, if we don't have unity feedback, we have H of S like this. This is non-H of S. Now, it's not necessarily equal to 1. So we will see what we can do. What we can do here is this way. We can add, H of S is this one. We can add -1, and we can add +1 here. This is +1. This is +1, and we add -1. When we add +1 and -1, in parallel, Shabab, they are going in the same direction. What we do, basically, if we are adding 0, صح ولا لا؟ لأنه they are in parallel, and block diagram, when they are in parallel, they add together. So we'll have +1 and -1. Is that right, Shabab? Do you agree with that? We add +1 and we add -1, 2 blocks. So, but when we add +1 -1. Yeah, this is what it is. Now we will combine this h of s and -1. We combine them in parallel. They are going the same way. They are going in the same direction. We combine them in parallel, like this. Parallel and then parallel. So combine this in parallel, we will have here this next step. This will be h of s -1, and they will be added. They will be added together. So h of s -1, now this gs, h of s -1, and we have the +1 feedback. Sorry, the +1, it should be here +1. Are we doing it -1? Yeah, the feedback is negative, sorry. +1, but it is feedbacked with -1. This is +1, okay? So here, as you can see, when we are combining this, can we take the equivalent of this one? Just we take this and this. Now these are feedback. G of s and h of s -1 are feedback. Can I take the feedback of this? And then I call this one GE equivalent. I can say GE equivalent. GE equivalent will be simply G of s over 1 plus this times this, it will be G of s times h of s -1. And I can replace this by G equivalent, like I'm seeing you. And this will be my block. Next block will be like this. Feedback with positive, as you can see, with 1. This is 1, unity feedback. This is the G equivalent. We found the G equivalent. And now this is one, my G will be G equivalent. If I have non-unity feedback, this will be my G, which is non-unity feedback. واضح شباب? Where G equivalent is given by this, J over 1 plus JS H of S -1, or H of G of S H of S minus G of S. Now we will be dealing with simply the G equivalent. Instead of dealing with G, we will be dealing with G equivalent. And what applies for the previous unity feedback will apply for the unit. Now, if you want the transfer function, the overall transfer function, it will be C of S over R of S, G equivalent over 1 plus G equivalent HS. At the end of the day, you end up by having C of S. The overall transfer function will be 1 plus JS times 2 H of S minus 1. As an example to that, they are asking you to, for the system shown, find the system type. This one, we have this equation. Here, H of S is not equal to 1, as you can see. This is H of S is equal to 1 over S plus 5. What is the system type? Can anybody tell me what is the system type here, Shabab? Yalla, question, please. System type. What is the system type? System type. System type, Shabab. From where we get the system type, we cannot say anything about the system type. We cannot say anything. We cannot say anything about the system type until we find GE of S. What is GE of S? G equivalent. Then the system type can be determined from GE equivalent. We need to find what is GE equivalent. We cannot say anything about GE equivalent. So the system type here, when we take GE equivalent, it will be this. And at the end of the day, we found GE equivalent like this. And you can see that the system type is 0 because now we have GE equivalent. System type is 0. So KP, the appropriate error constant now, since the system type is 0, KP will be GE 0. Always we look to GE 0. KP will be minus 5 over 4. And the steady state error will be 1 over 1 plus KP, or 1 over 1 minus 5 over 4. 1 over 1 minus 5 over 4, at the end of the day, you end up by having negative value here. Negative value means that the output go beyond the step input. if this is the steady step input, this is what it is. The error here is like this. So this is your response, and this is the error is on at top. This is ESS is equal to -4. This negative value of steady state error implies that the output is larger than the input step. The output here is larger, is on the upper side. There is one example left. I don't know. Do you want me to solve it? Shabab, I want to solve it now if you have some time. Can you spare just 5 minutes? If you spare 5 minutes, we will be able to solve it. In the feed-forward transfer function for unity feedback system is shown in the figure below. G of S will be K S plus A over S plus B squared. And you have unity feedback. We don't have to worry because unity feedback. Find the constant K, A, and B in order to meet the following requirements. Steady state error for unit step input will be 0.1, the damping ratio 0.5, and the natural frequency will be simply 10 radian per second. So the steady state error for unit step input, they wanted 0.1. This is the requirement. Now let's see what is the system type here. Our system type is from G of S, but we can calculate still. We can calculate E of S. E of S will be R of S over 1 plus J of S, which is 1 over S, 1 plus K. This is our equation here to find the E of S. So the steady state error, when you take S equal to 0, the limit S E of S will be simply this one, limit S times this guy here, 1 over S K S plus A over S plus B the whole square. S will cancel with S, here 0, here 0. You end up by having K A over B square, K A over B square, or B square over B square plus K A, which is 0.1. If you work on this one, you will find that Ka is equal to 9b squared. This is one equation. And we have two unknowns. We have three unknowns. We have K unknown, A unknown, and B unknown. We have three unknowns in one equation. So we need two more equations that we can get from the natural frequency and the damping ratio. Now we will calculate the overall or the closed loop transfer function, which is C of S over R of S. C of S over R of S is J over 1 plus JS. This is J over 1 plus JS, give you this equation at the end of the day. K times S plus A over S squared, K plus 2B times S plus B squared plus KA. Now we compare the denominator with the standard one, second order standard one. We'll find S squared plus twice zeta omega n S plus omega square n. And say that omega square n here will be equal to B squared plus KA. Omega square n B squared. Omega n, it was given to us as a condition that is equal to square root of 10 radian per second. So omega square n will be equal to 10. This is given. On this side, omega square n will be B squared plus KA. This is the second equation. We are getting the second equation. And we have twice zeta omega n. Twice zeta omega n will be K plus 2B. Twice zeta omega n plus K plus 2B. The condition, we have damping ratio is equal to 0.5. This means that twice zeta omega n will be equal to 2 times 0.5 times square root of 10. This is it. So 2 times 0.5 will be 10. 10 will be 1. 1 times square root of 10 will be square root of 10. And we have the third equation. So we have the previous equation number 1. This is the second, and this is the third one. Now we need to solve these three equations simultaneously. If we have Ka is equal to 9b squared from the previous equation number 1, if we substitute it into equation number 2, we'll get this. B squared plus 9b squared will be 10. And 10b squared will be 10. So B will be plus or minus 1. So if we substitute B is equal to 1 because we have two values, B is equal to 1 in equation 5 gives you K plus 2B is equal to square root of 10. So we substitute B here by value of 1. So the square root of 10 minus 2 will be 1.16 for k. You substitute in the this equation ka is equal to 9b squared. You will find a will be 9b squared over k, or 9 times b squared. B squared, it is 1. B squared will be equal to 1. So square root of k will be simply 1 over 1 over 6, gives you 7.743. So 1 over 1/6 for k, and a 7.743. For if you get b is equal to -1, when b is equal to -1, you will have the same thing, but you solve for b -1. This will give you هنا b is equal to -1, يعني minus 2b, it will be plus 2b. This will give you 5.16 for k, and it will give you a is equal to 1.73. Okay, Shabab, let me take the attendance. For those people who came late, like Akhuna Hussein, he's telling me that the time is up. I know, but I already asked you to give me 5 minutes. Hussein, until you were late, you were not here. You just came. You are saying this, but يعني أنا طلبت الشباب يعطوا لي 5 دقائق من وقتهم. I'll take the attendance شباب. I know. I'm saying, أعرف كل من واحد جاء on time ومن راه مصحصح ومن راه مسوي تحويلة ومن I know everything, don't worry. أهم شيء أرجو أن تكونوا في خير وعافية وصحة أبدان وافية إن شاء الله، والله يجنبكم إن شاء الله كل مكروه، ما تروحوا بعيد، وتتخرجوا إن شاء الله بالصحة والسلامة والهناء، ونفرح بتخرجكم، وإن شاء الله نفرح بزواجكم حتى بأولادكم إذا عشنا. منير علوة موجود، أهلين. بغالبي فيصل موجود، أهلا وسهلا. الملاح ماجد موجود.
موجود دكتور، حياك الله.
الله يحييك، أهلا بالشباب. أخطاني حسين
موجود يا دكتور.
حسين أهلين. المحمد يا عبد العزيز. عبد العزيز كيف حالك؟ إن شاء الله بخير.
خير الحمد لله دكتور. حالك انت؟
القحطاني عبد الكريم مشبب. الشهري علي أحمد. الشهري إن شاء الله تكون بخير. القرني علي. As I mentioned شباب في البداية، في بعضكم كانوا غايبين. There will be no quiz this Tuesday. خلينا لكم الوقت حتى تشتغلوا شوية في البروجكت. القرني علي موجود. أهلين القرني. الزهراني فارس كيف حالك؟ منور يا فارس العادة ما شاء الله.
الحمد لله تمام.
حمدان عبد العزيز الحمدان. الشريدة محمد. أهلين شريدة، منور ما شاء الله. العجمي مبارك. أهلين العجمي، أهلين. الطليحي يوسف كيف حالك؟
موجود يا دكتور.
كيف حالك؟ الله يبارك فيك. الزاير حسان، بشرني كيف أمورك؟ إن شاء الله بخير. العقيل الرائد عاقل ولا العقيل رائد، وهو موجود. الدرويش عبد الله. أهلين عبد الله، كيفك عبد الله؟ إن شاء الله بخير. العمدة حسين شرفنا. الشيخ حسين موجود. المحمدي دبيس
موجود.
أهلا بالدبيس، كيفك يا دبيس؟ إن شاء الله بخير.
الحمد لله بخير الله.
كيف الحرارة عندكم اليوم؟ مليحة ولا؟
فوق.
واو، ما تطلع برا، خليك داخل، وانا قلت لك خليك برا.
اكيد.
المحمدي سلمان كيفك يا سلمان؟ رد علينا يا سلمان. البشر علي. البشر علي، الله يبشرك بالخير البشر، ما دام موجود انت هنا شارة الخير ان شاء الله. الرشودي موجود؟ رشودي.
حاضر يا دكتور حاضر.
اهلين الرشودي، كيف حالك؟ ان شاء الله بخير.
يا حلو اللهم لك الحمد. كيف حالك؟
ناصر.
حاضر يا دكتور.
الله ينصرك ان شاء الله.
وياك يا رب.
عواد سلطان. العواد سلطان، كيفك يا سلطان؟ ان شاء الله بخير. السوبدي علي، كيفك علي؟ بخير. عبد اللطيف موسى، عبد رب النبي موسى، تمام موسى من ناحيتكم هناك؟ فهد. فهد كيف حالك؟ ان شاء الله بخير. الحمد لله. المحمدي يزيد كيفك؟ ان شاء الله تمام. خباز منتجب، اهلين خباز منتجب، اهلين عبد العزيز زهراني، كلكم منورين ما شاء الله. الصبحي نايف الصبحي.
موجود دكتور.
اهلا وسهلا، كيفك؟
خير الله يسلمك.
اخبار المدينه اليوم؟
الحمد لله تمام.
ايش معنى هاني مي تو؟
keep my name too.
يا ناديتك، مش محتاج ناديك انت بس.
الله يسلمك.
النور هنا ما من الكمبيوتر ما اقدر يعني انساك.
الله يسلمك يا دكتور.
ما اقدر انساك يعني.
الله يسلمك جزاك خير. المعذرة بلشناك يا دكتور.
لا عادي شباب.
مشكور.
مين اسمه شباب؟ مين ما سمع اسمه شباب؟ انتم تروحوا وانا اروح اسوي جريدنج للامتحان. مين ما سمع اسمه؟ نادر الله يهديك يا نادر. عبد العزيز الزهراني، اعتقد ناديتك ما عندك مشكله. هنا في واحد اسمه الحمدان عبد العزيز اللي ما اما الاخرين كلهم موجودين الظاهر.